Hello and welcome back to Algebra, the video series where we talk a lot about group theory and what we can do with it. And indeed, in today's part 20, we will look at an application of Lagrange's theorem. And I can already tell you, this one is known as Fermat's little theorem. We will formulate it in the general version for groups, but also in the special version for integers. In fact, you will see that this is a result you often have in number theory. However, as always, before we formulate the theorem and prove it, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Steady or Patreon, you can download a lot of additional material with the link in the description. For example, you find books, quizzes and PDF versions for the videos. And now, without further ado, let's immediately recall Lagrange's theorem in finite groups. There we just have to fix the group G and consider a subgroup U. And now the important notion we have there is the index of U in G denoted by this symbol. And by definition, this is the number of right cosets of U in G. And now Lagrange's theorem tells us that this index can be nicely calculated by the number of elements in G and U respectively. Namely, you just have to calculate the ratio order of G to the order of U. And as already mentioned, this works no matter which subgroup U of G you choose. Hence, this fraction here always gives us an integer, which means we have to care about the divisors of the order of G. In particular, if you look at the order of an element G in G, then you know it's a divisor of the order of capital G. And there you see that some number theory comes in because we suddenly care about divisors of a natural number. Moreover, here we can also use our knowledge that the order of an element is related to repeating the group operation until we reach the identity element. This simply means that we can write G to the power of the order of G and get the identity element E out. And in fact, this is almost already Fermat's little theorem in group theory. And as already mentioned, this one is formulated for finite groups G. And now we take an element G and repeat the group operation. And we denote that by using the power notation, so we have G to the power of the order of the group G. So we have the element G with itself in the group operation as many times as the order of the group tells us. And then it does not depend on which group we actually choose, because we always get out the identity element. And usually the neutral element in the group is denoted by E. So now this is a nice formula and it actually holds for any element in the group. So this result here is really nice because it tells us that repeating the group operation as many times as we have elements in the group brings us always to the identity element. So it does not matter from which element we start. And in fact, this is really easy to prove because we already know that the order of an element satisfies this equation for sure. So more precisely, if we put the order of G into the power here, then we get out E. However, now Lagrange's theorem tells us that there is a relation between the order of an element and the order of the group. Namely, the order of the group can be written as a product where one factor is the order of the element G. And let's simply say that the other factor is a natural number m. So this comes from Lagrange's theorem, and now we just have to combine both facts. So this simply means that we can substitute the power in the formula by this product. And then obviously we can just use the properties of this power notation. This simply means that we can write this repeating of the group operation in two steps. However, now we already know that in the first step already we have our identity element. In other words, we have the identity element E to the power m, which is the identity element again. And that's it. This is the whole proof of Fermat's little theorem in group theory. So quite simple, because we have already done all the work before. However, at this point you might ask, how does this general result translate to number theory? Indeed, for this we have to take a special group G, and you might already know it comes from our integers with the modulo operation. But here we want to do something new, namely we want to look at the multiplication we have on the group given by the integers modulo p. And you already see I call the number p because it should be a prime number. And now we consider our group integers modulo p. In fact, this additive group we have already discussed a lot, and we know it consists of exactly p elements. And to be precise, we would write the elements as equivalence classes. So then we have the equivalence class of 0, 1, 2, and so on. And in fact, the last one is then the equivalence class of p minus 1. And here please don't forget that we write the group operation as an addition, and the equivalence class of 0 is the neutral element in this group. But now, additionally to that, we also want to put a second operation on this set, which we call a multiplication. And the name here should make sense because it comes from the original multiplication on the integers. And this should also already tell you that the definition of this multiplication is quite simple. Let's simply take two equivalence classes, one represented by k and the other one by L. And now we want to define the meaning of a multiplication of two equivalence classes. And obviously this can be done by just multiplying k and L. So we just have the ordinary multiplication of integers, and then we just take the equivalence class of the result. So the only thing we have to check is that this definition does not depend on the chosen representative of the equivalence class. And I don't have to write that down because it's quite easy to check. So what we get is that the multiplication on this set here is well defined. And moreover, we also immediately get the identity element for this binary operation. Indeed, by definition, it has to be the equivalence class of 1. Therefore, the next question should be, do we also have inverses? So do we have a group in the end? And there I can already tell you this does not work in general because we have a 0 involved, and 0 times anything is always 0. But perhaps it could be that if we exclude this annoying element, then we could have a group. And in fact, in the case that p is a prime number, then this is correct. So in other words, we get a multiplicative group as well. And moreover, there is a common notation for that because we use the original modulo notation and a star or an x in the power. So if you see that symbol, it should remind you that we care about the multiplication on this set, and we only take the elements that have inverses. And indeed, if we have a prime number p here, then only the 0 element has no inverse. Indeed, the existence of inverses actually also comes from number theory. So maybe you already know that it comes from Bezout's identity. It just tells us that for any two integers a and b we consider, we can always find some coefficients x and y which are also integers, such that the linear combination gives us the greatest common divisor of a and b. So more concretely, we have x times a plus y times b, and this one is equal to the integer which we write as gcd. So it should be a common divisor between a and b, but also the greatest one. This one is well defined, and you might know how to calculate it by using the Euclidean algorithm. In fact, Bezout's identity immediately follows from the complete Euclidean algorithm. And that's why I don't want to talk too much about it, because we just want to apply this result to our group here. So you know we consider a prime number, which means that the greatest common divisor is quite simple. And moreover, the other numbers we are interested in can be chosen to be smaller than p. This means that our number k here lies between 1 and p minus 1. And this immediately implies that the greatest common divisor between p and k is equal to 1. Hence Bezout's identity looks quite simple in this case. We just find integers x and y with the property that x times k plus y times p is equal to 1. And there you see, if we want to make it tidy, we would bring y times p to the right hand side. In other words, x times k is 1 plus a multiple of p. So in short, it's just equal to 1 mod p. Hence, seeing everything with equivalence classes, x times k is equal to our neutral element. So there we have it. The inverse of the equivalence class of k is given by the equivalence class of x. So this is the justification that we actually have a group here. But this also tells us that we can definitely apply Fermat's little theorem for this group here. And you already know, in order to do that, the only thing we need to know is the number of elements in the group. But this is quite simple, because as we have already said before, we only exclude one equivalence class, namely the one with 0 in it. Therefore, we have exactly p minus 1 elements left. And now let's simply apply Fermat's little theorem, and as you can see here, this was the general formulation from before. So let's substitute the symbols. First, the order of g is p minus 1. And on the other hand, the identity element is the equivalence class of 1, and g is just the equivalence class of an integer. And maybe to keep it simple, let's call this integer a. However, by the reasoning from before, we cannot go to all integers because the greatest common divisor should be equal to 1. So it just means that a should not be a multiple of p, because otherwise this equivalence class would be the 0 equivalence class. So with this small restriction, we can translate our equivalence class back to the modulus operation. So it just means that we have a to the power p minus 1 is equal to 1 mod p. And this one is exactly what we call Fermat's little theorem in number theory. And now sometimes one does not want to mention the small restriction we have for a here, and this one we can also easily get. Indeed, just consider the equation with the two equivalence classes here and multiply both sides with the equivalence class of a. Then we have the power p on the left hand side and the equivalence class of a on the right hand side. And now the advantage is that this equation definitely also holds if the equivalence class here is given by the 0 equivalence class. This is quite trivial, but it helps us to extend the formula from before. Namely, now we can definitely write for all integers a and z, we have that a to the power p is equal to a mod p. So this is quite nice. This is the formula you can remember as Fermat's little theorem. However, now I hope that you have learned that it actually follows from a general result in group theory. But it still gives us a nice result for integers and prime numbers. So I think this is a good closure for this video, and I would say let's meet in the next video again. So have a nice day and bye bye.